morning and welcome. Today I want to talk about when we got the first evidence for the Continental crust, and I think we're going to spend most of the talk on when, and sort of I'll leave the how as an open question because we don't really know, but what I want to establish today is when do we think we got the first evidence of something that you can call a continental crust, so something that looks like a granite. If you remember your handout from last week, these are the high silica rocks. Basically what you're standing on today is continental crust, and the stuff below sea level is the oceanic crust. So when is the first evidence for a high silica rock, something that isn't a basalt on this planet? The web address here, I'll see if I can email it out. This is where I'm uploading the lecture slides. So the first 3 lectures are uploaded to that website, so you can go there and look.
Come January, you may take advantage.
Is the lighting good?
It's okay, yeah.
Good morning and welcome. Today I want to talk about when we got the first evidence for the continental crust, and I think we're going to spend most of the talk on when, and sort of I'll leave the how as an open question because we don't really know, but what I want to establish today is when do we think we got the first evidence of something that you can call a continental crust, so something that looks like a granite. If you remember your handout from last week, these are the high silica rocks. Basically what you're standing on today is continental crust, and the stuff below sea level is the oceanic crust. So when is the first evidence for a high silica rock, something that isn't a basalt on this planet? The web address here, I'll see if I can email it out. This is where I'm uploading the lecture slides. So the first 3 lectures are uploaded to that website, so you can go there and look at them if you want to look at the website. I unfortunately did this after I sent the handout for making copies, so the link didn't get included there. So I wanted to quickly address a question from last week where someone in the audience asked how far off magma ocean simulations are from reality, and I found this paper which came out in 2017, actually came out a couple of weeks ago, and I just saw it during the week, and they made this beautiful plot of here is convective velocity in your magma ocean, and here is sort of the crystal size that they're thinking of, and here, this gray box at very large crystals moving very slowly is what they can simulate, and here's what we think would be a realistic magma ocean. So you can see that the models are simulating things that are tens of kilometers and moving, incredibly slowly. Whereas we think in a real magma ocean, you would have things that are centimeters, millimeters in size, moving at maybe over 100 meters a second, so getting into kilometer per second territory. So very high convective velocities. And I don't really need to pick on them. They're not unique in having this problem. The difficulty in going from here to here is that you need a lot more computational power. You need here, you can use a lot less grids you can use a lot coarser spatial resolution to characterize your Earth. In order to do this, you're going to have spatial resolutions in your model that can track things that are a millimeter, and that's much harder. The time step difference, right? If everything's moving really slowly, you can simulate one time step and then jump ahead to a future time that's very far in the future, and stuff won't have changed much, but if everything's moving very quickly, then you need to put in a lot more time steps, and the computational power isn't there yet for this, so basically that's where we are, that's where we'd like to be, and this is in both dimensions a log plot, so we're really far off in these models. You go forward. So here are 2 different of their simulations for different sizes. So these are, for one is going to be for bigger grains, one is for smaller grains. They put it in this characteristic size, which you don't have to worry about. So basically here's with the smaller end of their crystals, here's with the larger end. And you can see in things like here are velocity gradients, you can see that everything's kind of blurred out. Here are the temperatures, hot to cold, hot being in red, and you can see different behavior. Here they're plotting out melting, and here, red is 100% melt, and blue is 0% melt. So you can actually see that when you have the large, everything's kind of spreading out, whereas in the other simulation, everything's clumping together. So these are differences that are likely to matter, and they make very different looking physical pictures, especially in terms of temperature distributions and how melt is behaving. So that's just to give you a sense of how far the computer modeling has got to go after last lecture. So today, what I want to talk about is actually when do we think this planet first got its continental crust? So this is a figure from a review paper about 8 years ago, where you're looking at the area preserved in tens of millions of square kilometers of continental crust as a function of age. So we have a lot of crust that's really young, right? If it's getting created, it doesn't have a lot of time to be destroyed. And then we sort of have this drop off, and the oldest, this goes back over, the oldest rocks are really 4 billion years. So basically after this should go to 0. And these are from 2 different models from the late 60s and the early 80s. And this picture hasn't changed since the oldest rock is still right about 4 billion years old. And the other things that you can see in here, it's plotted, heat production is decreasing, so here's when the planet formed, if things were hot. So you might think that if there was tectonics back then, that the tectonic plates would be moving really fast. And maybe you have a really high relative recycling rate. So maybe you're just really efficient at destroying this crust. But the punchline that I want you to take home is that if we just go by the rock record, we have to say that the oldest rock that points us to a continental crust is about 4 billion years old. And then before that, we don't have any. One of the questions is then, does that mean it didn't exist, or does that mean that the planet having plate tectonics simply destroyed it? So we're going to have to go look at other things, isotope systems or zircons, to try and fill in this age period here. So while the area of preserved continental crust is one possible model, so here's the Hurley and Rand. So this is now relative percent volume continental crust. This is relative to today. So today, plotting over here, if you look at the top axis, it's 0. This is us today. Every model goes to the present amount. The model that is simply based on the preserved abundance, saying that the planet is accurately preserving things, is the Hurley and Rand model. It's this blue line here. And it's saying basically, look, you don't have any continental crust, you don't have anything, boom, it takes off towards present day. So that's the preserved record. Other models are saying we had a lot of continental crust quickly before the planet, when the planet formed, shortly after the formation of the planet, 4.35 billion years ago. And then it went up to 100% and stayed there. One model even predicts an overshoot that you're now destroying it. So the punchline here is there's really, as of 2009, very little agreement in how much continental crust there is as a function of time. If you were to draw your own curve through this, it's really hard to find a curve that hasn't been taken yet. So there's a lot of debate. People get at this from different systems. And I want to say that this is a much harder question to address than the one that I want to go after today, which is the one I want to go after is, when can we say that there was some continental crust? So can we at least try and narrow this space down by saying, we have good evidence for continental crust 4.3 billion years ago, so this curve here that says there was 0 is not a viable model. So can we at least try and put a spot saying, it can't be 0 at this point in time, it must be above that, because the arguments about how much there was, as you can see, the rock record can point you to a diversity of opinions. So, the classic view, right, there's a lot of these curves even recently, that there was an early there was no continental crust, and then you're slowly sort of making the continental crust through time, so that everything was mafic, and then it slowly became a felsic crust over time. The fact that we have old zircons does suggest that there was some felsic crust in this older than 4 billion year period, but it doesn't tell us when it formed or how much, and you can even sort of argue with that. We'll get into this in future. The Archean rock record, so if you're looking at whole rocks, the Archean rocks are all screwed up, basically. So if you're looking at really old rocks, they've experienced, right, if the rock is 3.8 billion years old, it's experienced 3.8 billion years of adventure of life. And that means it's probably not a good signal. We only have zircons from the 4 billion year plus period, and this has led to this sort of paucity of evidence and this sort of traditional view has sort of led to a lot of models. To show you a different example, this is from 2015, so that I'm not just quoting old literature actually. This is from 2015 saying, you know, this is a really sort of complicated model that I don't necessarily want to get into all the details of, but they're saying, you know, look, the crust was mafic, and then we got a continental crust, and then through present day. So this here is basically how much, what the silica concentration was. So higher means more felsic, lower means more like salt, more mafic. So they're saying, look, the crust was mafic, and then it slowly became a felsic crust, so that, you know, you're taking one of these sort of curves here. This, in one particular place, was proposed in Nuvvuagittuq in northern Canada on the eastern shore of the Hudson Bay. I'll show you a map when we get to the samples that I'm going to analyze for this talk. They said, so this is the part per million deviation, part per million, so this is 5 parts per million, of the 142 neodymium to 144 neodymium isotopic ratio from what the mantle looks like. So if you pick up a mantle rock and you measure some ratio of 142 neodymium to 144 neodymium, when you measure these samples, you're saying that there's a 10 part per million difference. So a really, really small difference, but it can be measured quite precisely. And their claim in this paper is that the reason for the 142 neodymium variation is that there was 146 samarium that decayed to 142 neodymium. And if you change that elemental ratio while 146 samarium is alive, it's got a half-life of about 70 million years. So while it's alive in this early period, that you can make these isotopic differences, and you can then get them into younger rocks. So these rocks formed at 3.8, at 2.6 billion years, and they're sort of preserving this old anomaly, saying that the samarium-neodymium ratio was significantly different from the mantle. And they're actually saying that this precursor was mafic because they claim that, look, it's these samarium-neodymium ratios here in the tiny font, it's 0.135 to 0.165, really explains their data really well. And their claim is that this was a mafic crust 4.3 billion years ago that then became more felsic over time. So they're basically in support of this model here. And they also make the claim that because felsic rocks have a different samarium-neodymium ratio, they would have evolved to a very different place. And they can say, look, this couldn't have been a felsic continental crust. Back then, it must have been a mafic crust that slowly formed, turned into a felsic crust over, you know, billions of years of slow evolution. So this is to sort of make this schematic. What the people are doing is saying, we measure an isotope ratio. This isotope ratio has input from a decay system. So in this case, lutetium is decaying to hafnium. And so variations in this hafnium isotopic ratio can let us infer that the lutetium-hafnium ratio was different than, say, the bulk mantle or a chondritic reservoir, or some reference reservoir. And from this, we can conclude something about the silica content of the crust. So if you infer a low lutetium-hafnium ratio, you would say, well, this is a really high silica source. So a granite the claim is has a really low low lutetium-hafnium and a high silica, and the basalt has a high lutetium-hafnium ratio, and that these isotopes track this. So this is a really indirect argument, is the point I'm trying to get across. In the samarium-neodymium case, you measure neodymium, you can do 142 or 143, it's equivalent for this purpose. That lets you infer a samarium-neodymium ratio, and then that lets you infer a silica content. Strontium works the same way. You measure a strontium isotopic ratio. From this, you can infer a rubidium-strontium ratio. And from this, you can measure a silica content. So in this case, what you're doing is, if you look on your handout, I showed you 2 isochrons. And in those 2 isochrons, what you can see, one is an example where you can plot up different samples of different elemental ratios plotted on the x-axis, so the rubidium-strontium ratio. And over the same amount of time, they will evolve to different strontium isotopic ratios. So if you knew the age of the rock, and you knew what the strontium isotopic composition is, you can basically read off what the elemental ratio is. And that's all what these models are doing, is saying, we roughly know the age, we roughly know, we can measure the isotopes, and so we can infer the x-axis. And this is all fine and good, but it's going to get, this step especially, I'll show you, gets a little bit messy. So let's, to start with, work our way through the lutetium-hafnium system. And this is similar for what I showed you during when we were talking about the moon. So in this case here, you have the 176 hafnium, 177 hafnium ratio. And you can see from the lovely equation down here that 176 lutetium is going to decay to 176 hafnium. So your 176, 177 ratio at any time is the initial value in the solar system when the solar system formed, plus whatever the lutetium-hafnium ratio is times the age of the sample. So if you wanted to study chondrites, these are the undifferentiated, unmelted meteorites, you're going to get an evolution like this. So 4.56 billion years ago, the solar system formed, you're at the initial value, and then as you get to more recent times, more of the lutetium is decayed to hafnium, and so you're working your way up this line, and so a billion years ago, chondrites would have measured to here, and if you were to correct them for the known age, you'd actually then basically be able to infer this value. So, if you have a chemical event, something like you are now melting your planet, you're melting your body, and you're forming a crust and a mantle, you're going to have the chemistries evolve differently. So the lutetium-hafnium ratio of the enriched liquid, by that I just mean crust, is going to be lower than the lutetium-hafnium of the chondritic starting point, and the mantle that gets left behind, this residue, is going to be enriched. So if you can take a sample and measure its age, and you can infer something about when this event happened or what the chemistry is. So we get a zircon that's 2.5 billion years old and measure its hafnium isotopic composition. We can say, you plot here, you're not on the chondritic line. So at some point previously, you must have separated from this reservoir, and that gives you evidence of a crust. And since the lutetium-hafnium ratio is related to what the silica content is, and the lutetium-hafnium ratio determines basically the slope of this evolution line. If there's no lutetium, right, you're just going to be flat forever. There's no ingrowth. If you have chondritic, you're going to be here. So the claim would be, a granite separated here would evolve along a very shallow line, and a mafic rock separated at some time would evolve pretty close to the chondritic line. So, in part because isotope geochemists just like messing with people, they decided to take this plot and rotate it. Because we always want to reference everything to the chondrites and not to the initial value. This is a moving target, so what we're going to do is say, well, these ratio deviations are tiny variations, so we're going to take the part per 10,000 difference, this is epsilon, and then we're going to rotate it and always reference it to the chondritic reservoir. So basically what we're going to do is make this line flat. So we're going to make this line flat, and if you have a constant isotopic composition, lutetium-hafnium of 0, this is what the time axes are reversed here. That's really important to notice. The lutetium-hafnium of 0, so a constant hafnium isotopic composition evolves along this line here because it's getting progressively more different and looking more negative relative to the chondrites, which are plotted along 0 here. So these are a whole bunch of terrestrial zircons. Each one of these here is a zircon. They were all found in Western Australia, but that doesn't matter. You can take a more global composition. Here are the zircons between 3.4 and about 4.3 billion years ago. And the first thing that you notice is they don't all plot on 0. So they're giving you evidence that some sort of chemical event happening, you have formed some sort of a crust. And they plot in a huge variety, right? They don't all just plot on one line. So you're not just tracking the same events. You're not just saying, look, we separated a crust of one composition here. It's going to evolve along some imaginary line here with my laser pointer, but what is showing you is a sort of fanning out pattern. So it's telling you that there was maybe a whole lot of diversity, and it's telling you that some of these data points are really close to the lutetium hafnium equals 0 line. So these are zircons that separated from a reservoir with a very, very low lutetium hafnium ratio, or, to put this in silica content, very high silica content. So the argument is then that these zircons here are giving you evidence for a really early formed continental crust, right? If you just took and drew this back, projected this back, you're ending up 4.4 billion years, or even older possibly, with very low lutetium hafnium. So you're having a felsic crust, and you're doing it very, very early in the planet's history. That's the story from the hafnium isotopes, but the lecture unfortunately can't end here because life isn't actually that simple. These zircons are old, and I've shown you what we've looked at the uranium-lead system in a previous lecture. So just briefly, uranium decays to lead. There's 238 decaying to 206. There's 235 decaying to 207. So you get 2 clocks for every zircon mineral that you analyze. They have the same chemical behavior, 2 uranium isotopes decaying to 2 lead isotopes, so they're telling you the same thing. And if your sample is perfect, it's going to be at like this star here. So that's where the sample starts off. Like if everything is perfect, then you can get the hafnium isotopes accurately. The problem is, if you were to lose some lead, you will be moved to younger ages, and you might move off this line. But because this data point is really close to the line, you might make the measurement and say, oh, my uranium lead age is perfect, I'm right on the line, even though you're a little bit off, and then you're getting an age that's too young for your zircon. So what this does is it drags, if you look here, this is epsilon hafnium, this is 207, 206, this is the age of the zircon. As you're moving from the original age down to the more disturbed age, saying it lost lead here, you're dragging the epsilon hafnium down with you. So the argument could be that these data points here didn't start life out down here, but they moved along this line and are plotting here, because this is what happens if you are making a mistake in your age measurement. If your zircon's age is actually older, like let's say this zircon should have been 4.4 billion years, it will move on a line parallel to this, up in this spot, plot here, and you'd say, oh look, it was a mafic crust. That this inference that there was a low lutetium hafnium ratio, it could also be an analytical artifact from the difficulty of dating these old samples. So, in fact, such a claim has been advanced. It was advanced in Kemp et al. 2010, who said, if we look at these zircons, not all of them look good to us, only some of them look good to us, and we're going to throw out any data point we don't like, essentially, until we end up on a line that has a lutetium hafnium ratio of 0.02. And then they said, look, all of the points that we call reliable are on this nice line, and this nice line is consistent with a mafic reservoir, and that there's evidence for a felsic crust is essentially an artifact of analyzing crappy samples. I'm being a little facetious about their criteria, in part because that's what they did. They don't really describe what makes a good versus a bad sample. They simply sort of laid this claim out there, that these are the least disturbed. Well, this now makes a really nice testable prediction that everything was mafic back then. We've got this nice line, everything was mafic back then, and this is in support of this sort of O'Neill et al. View. That the crust, it was mafic and slowly sort of became felsic. So these are, in this inference with the arrows, these are the known unknowns. People are arguing, are the samples altered? Did you make the measurement correctly? Can you date your samples? This is all fine and good. People have been debating this in the literature. The part that isn't really debated, as Rumsfeld put it, unknown unknowns, are whether or not the lutetium hafnium ratio actually corresponds nicely to a silica content, samarium, neodymium, rubidium, strontium. And this is a plot that you all have on your handouts, on the back side, I believe. And this is a compilation out of work. The compilation was done by my collaborator, Brennan Keller. And the blue lines here are the average values for igneous rocks that you find on the planet today. So these are young modern rocks that haven't had time to be altered or disturbed, so they're as nice an example as you can get. And then you have, what you have plotted on X is the silica content of the rock, and then I plotted the samarium neodymium, the rubidium strontium, and the lutetium-hafnium ratio. And what do you notice about the lutetium-hafnium ratio as a function of silica? Is it always going in one direction? No, right? It's going, first it goes down, right? This is the sort of the classic story with the arrow that I drew. Mafic rocks at a low silica content have a high lutetium-hafnium ratio. And then, great, the lutetium-hafnium ratio is dropping, silica is increasing. That's great. That works up until about 78% silica, and then the entire pattern reverses. Samarium neodymium, similar problem. The issue with this is, first I thought for sure that this was an error in the compilation, that maybe somebody just really liked, there aren't a lot of, maybe somebody really liked sampling some weird rocks, and so I thought for sure that this was an error when I first saw the plots, and I was like, ah, that's funny. So I went and looked, and in the southwest of the US, there's a beautiful place called the Spirit Mountain Battle. This is a big magma chamber that is preserved in the whole variety of silica contents, from the lowest here being about 52% silica, all the way almost up to sort of 78% silica. So those are the open symbols that you see. And you can see that in a single magmatic system, you can preserve the same behavior that the global compilation shows you. So that was comforting. The samarium neodymium is a little offset and basically flat, but this presents the same problem, right? You can't say, oh, a low samarium neodymium ratio is a felsic rock, because you can get more or less flat behavior. The filled symbols are from a rhyolite. This is the end member of high silica volcanism. So these are volcanic rocks that are really high in silica content, and they basically, plot at values where if you were to go through and say, oh, look, I measured and inferred the lutetium-hafnium ratio of 0.1, this is mafic, or really felsic. So that's sort of the issue, is that people are inferring this axis and then saying, look, if I look here, I'm done. Wait, there's a second sort of population of samples that actually works for this, that is relatively unexplored in this. The system I'm skipping over is the rubidium-strontium system, and it has a couple of really nice features. For one, I'd like you to notice, this is now a log plot, right? These are ratios from 0.04 to 0.12, relatively small changes, 0.16 to 0.24, really small changes, basically constant. Rubidium-strontium system in igneous rocks, so rocks that nicely crystallize from a magma chamber, or in a volcanic setting, they start life at 0.1 for sort of 50%, and then go up to over 100 by the time you get to the rhyolite at 78% silica. So you have a lot more leverage here, right? This is a lot easier. You get a lot more bang for your isotope buck, because if you're trying to infer a rubidium-strontium ratio, if you make an error by a factor of 2, isn't really going to change your story, right? You're either going to see a sort of a high one for the high silica or nothing for the low silica rocks. Yes?
The squares on these plots, do they represent actual data points?
Yes.
Or are these the outliers?
The squares are actual data points collected from rocks from the southwest of the US.
Okay, then where do the curves come from? Because the correspondence between the data points that you're showing and the curves that are on the graphs seem to have no correspondence at all.
The curves are an average for that silica content of every rock that's been analyzed and put in a huge database. So this is a small set of data here that was from one magmatic system. The curves are an average of everything. So that's why they are not fits. So the curves are not fits to the data that is shown, because this is a global compilation. This is basically every rock that's ever been analyzed.
Right, so the data points that are on there correspond to the silica percentage that is in the one axis, correct?
And to whatever that lutetium-hafnium or rubidium-strontium or samarium neodymium, depending on which plot you're looking at. Right? So the data points themselves tell you two pieces of information. So this is a rock with a lutetium-hafnium ratio of 0.04 and 53 weight% in silica.
Can you do the same thing for an actinide set?
For what?
PB, for instance.
Sure.
Do you have anything to show that?
Nope, because they're not really used to do this kind of work. So these three systems here are what are used to infer the silica content. So you could, in principle, maybe say that the uranium-lead ratio will tell you something, but those aren't sort of the systems that are commonly used for this, because the uranium-lead system is great for actually dating your rock rather than doing this sort of tracing type work.
Do you get anything like that from the light elements like potassium?
The potassium content scales quite well with the silica content. I can dig out plots at some point for this.
Just give us a reference, somewhere.
Yeah, actually, if you look at Keller et al. 2015, so there's the reference.
That's in there? Okay.
That's the data is from there. He actually makes those plots in there. So the potassium content goes up with the silica content.
Thank you.
So the punchline to this is that where people are using systems, the lutetium hafnium, the samarium neodymium system, not because they're actually great for this purpose, but because they are the systems that can be measured and the systems that are not as easily altered. The reason that no one uses this great system in whole rocks is that rubidium is about the most fluid, mobile element that you can get. If your rock sees some water, odds are your rubidium content has been changed. It is really, really, really mobile. So if you pick up an old rock, the rubidium-strontium ratio is going to be something, but it wasn't what it was when that crystallized. So you're going to have huge issues trying to do this in the whole rock record, and there's no good mineral to measure. Right? I've talked a lot about zircon. Zircon for inferring this ratio. Zircon is great. It's one of the most robust, tough minerals that we know. It's really resistant to metamorphic effects. To if you make it a little bit uncomfortable, the zircon goes and says, "Ah, that's nothing. I'm going to be really cool about this." So that's why this system is used. This in whole rocks is one of the less disturbed systems, but it's not great for this kind of work. So, lutetium, hafnium, samarium, neodymium, not monotonic, they're not simple functions of silica, so you can't use them to infer silica. So we need a new approach. So let's go to Nuvvuagittuq, which is up here. So we're in Chicago, down here. I think you have to take like 7 flights to get here. I haven't been. One of my collaborators, Beth Ann Bell, went up here, and I think she went from LA. And you have to hop around until you can actually get here. There's not a convenient direct flight. So it's kind of a difficult place to get to. These are the rocks that preserve these anomalies. So we're going to look at a different mineral in zircon in these rocks to try and look at the strontium isotopes. So just to refresh, right, the claim is that based upon the whole rock neodymium isotopes, the crust that formed is separated from the mantle at about 4.3 billion years ago, and it must have been mafic. It could not have been a felsic crust. And we're going to try and look at this. So the first thing that I want to do is examine this claim based upon the previous figures of the claim that a felsic reservoir, a felsic crust, has a samarium neodymium between 0.1 and 1.2. So these are the labels on the plot from the previous paper. And this is what happens when you sample that same global database and say, I have samarium neodymium ratios between these values. What do the silica contents of the rocks that have these samarium neodymium ratios actually look like? Well, overall, I'd say that's not bad for calling this felsic, right? Most of the rocks are around 65, 70, 75 weight % silica. A couple of outliers down here, but when you're doing something, working on these rocks, that's a pretty good signal, I'd say. That's a good claim. There's what it looks like when you look at the mafic. What they claim is they say mafic rocks have between 0.135 and 0.165 in the samarium neodymium in this elemental ratio. But if you then sample this database and look at what kind of silica contents do rocks in between these two samarium neodymium ratios have, you get a whole lot of rocks, that are really felsic, right? This is not a great selectivity tool. You don't just see a peak here at low silica values. You can see everything. So their claim that this was mafic is not actually supported by the data if you were to go to take a look at a global database. So people have also done hafnium isotopes right here. Again, this is the sort of the epsilon hafnium. Here's that chondritic reservoir. This is 0. Lutetium hafnium 0, so constant isotopic composition again goes along this line. This is the age of when the zircons form. And here are these Jack Hill's least disturbed zircons from the Compton paper that I pointed to, plotted here. And again, the claim is, look, everything in Nuvvuagittuq has between a lutetium hafnium 0.02 to 0.03. And that this is characteristic of a mafic crust. You go and you play the same game and say, we're going to sample our global database for things that have this lutetium hafnium ratio, 0.02 to 0.029, their exact proposed limits. About 2/3 of the rocks are mafic, and 1/3 of the rocks are highly felsic, peaked at about 75%. And that's that U-shape. That's a feature of that U-shaped distribution that I showed you on the back of your handout. So the basic point is, the data can't actually tell you which of these peaks you're at. A felsic crust can give you the same signature here as a mafic crust. So the interpretation that this crust was mafic is actually a claim that is not supported by the evidence if we go and look at these nice global databases. This generally comes from people looking at a handful of samples in their field, in their area, and saying, look, in my field site this is true, so I'm just going to make this claim. But you're inferring an event that happened before the rocks crystallized, so it's not clear what relevance that has, and you should be using a much more globally representative view, such as the one that I showed you on the back of the... So let's see if we can use the rubidium-strontium system, the middle one, where there's this great isotopic leverage, where there's this great variation in rubidium-strontium ratio, to infer something about the silica content. I already told you we can't measure the system in whole rock, so we've got to get creative here. And there is a mineral called apatite. Bones are apatite, so all of your bones are a form of apatite. And in nature, so this is a calcium phosphate, so it's got calcium, phosphorus, and calcium and strontium are incredibly similar from a geochemical point of view. So I showed you in a previous handout sort of what the geochemical behavior is. Strontium likes to substitute for calcium. So a mineral that's got a lot of calcium in it, you're likely to find a lot of strontium. And apatite, because of its crystal chemistry, really doesn't like rubidium. So this is a plot, these are experimental samples, so somebody crushed up some starting materials, grew apatite in a little capsule and said how much rubidium and how much strontium goes in relative to the melt. And this sort of funny system is, this is how much an apatite prefers strontium over rubidium from a given melt. So these here are the experiments for silica. There's not really a trend here, it's just a way to plot up the data. And this is basically saying that in this experiment, the apatites preferred strontium over rubidium by a factor of 1,000 to 1. So it took 1,000 times more strontium than rubidium. Here it was 400, here it was 10,000. So apatites are fantastic because they're going to take a whole lot of strontium and not a lot of rubidium. So if we can know the age of the apatite, then we have this strontium isotopic signature. We don't have to worry about what has happened to it since then. We don't have to worry about there being rubidium and growing in and having to correct for that. So we can just get this great recorder of what the strontium isotopic composition was in that melt at the time that apatite crystallized without having to worry about later corrections. People have done a whole lot of work that if you take an apatite from a rock where the rock itself has been altered, say by having warm water go through it, the apatites are relatively undisturbed and will accurately preserve their signature. And in this case, we're going to make this even better because our apatites are included in the mineral zircon, which is a nice robust. So these apatites come with protective armor. And the zircon is really easy to date. So we're going to date the zircon, we have apatites inside of there, and we're going to figure out what the strontium isotopic composition is of that apatite to infer the silica content. Yes?
Do you get enrichment at the new melt temperature?
Sorry?
Do you get enrichment of in other words, a shift from rubidium to strontium at a near melt temperature?
It is not. You will get changes as a function that rubidium-strontium ratios in melts will change as minerals crystallize out of the melt. So if you go to a lower temperature, you will have changed it because you're now crystallizing different minerals out. So
what I'm saying is, at a near melt temperature, some of these crystals will be remelted, and they will then recrystallize. And depending on the concentration of strontium versus rubidium, you get enrichment with respect to the crystal structure because the crystal is more stable with the strontium than it is with the rubidium, right?
the crystal itself the apatite crystals will effectively not take any rubidium. They will only take strontium. So if you have a melt that's got a lot of apatites and you melt it, then you'll release a lot of strontium into the melt and you can change the melt chemistry. If you then crystallize apatite from it, you can pull that strontium out of the melt and put it into the apatite. So,
is there a significant difference in the melt temperature or the melting point, if you will, for those crystals that contain rubidium as compared to the ones that contain almost all strontium?
the rubidium is an element that is going to go into minerals that crystallize very much so at the end. So very close to when you run out of melt. So at the lower melt temperatures. So as a melt tends to cool and you evolve it by crystallizing other minerals out, you drop the rubidium to strontium ratio in that melt will change. But all of these issues are sort of irrelevant because to this purpose, because we're trying to trace an event that happened hundreds of millions of years before the apatite crystallized. The magmatic timescales are on the order of 10 to 100,000 to a million years. So whatever is happening during that melt window is practically instantaneous on the scale that we're trying to study this. The half-life for rubidium is on the order of 50 billion years. So it's a really long half-life system. So a little bit of changing during the melt evolution while this is crystallizing, it's so far down below what we can, the measurement precision, that we don't have to worry about this. So this is a picture. This is an electron image. This is a backscattered electron image taken in an SEM. So there's a 50 micron scale bar. Here's an apatite, and the primary problem with this picture is that the apatites are really small, so you don't get a lot of strontium to analyze. There's some other minerals in there too, quartz, there's some biotite, so you can find a whole lot of goodies in your zircons, and in a future lecture we're going to talk about what some of these other inclusions can tell us about melt chemistry. But today we're just really interested in using the strontium in this apatite to trace something about the history of that melt, in this case these zircons are 3.8 billion years. We're trying to understand this 4.4 billion year event because of its evolution prior to this by looking at the strontium isotopes. So these analyses were performed by, that we're going to talk about, were done by me here in Chicago using the Chicago Instrument for Laser Ionization. It's a unique mass spectrometer one building over. And it has a spatial resolution of about 1 micron, so these apatites are actually big by the scales of this instrument, so that's a good place to start. Here again, backscatter electron image. This was just their demonstration saying, look, we can make really tiny holes. And I now want to spend some time looking at how this instrument works. So you take your sample, this is just a very schematic view, you take your sample, so you take your zircon with your apatite, you put it in, we shoot a laser at it to remove some materials. This is going to desorb some material and basically make a cloud of secondary particles. This isn't to scale. This cloud is a millimeter or so across, or 2 millimeters across, sitting just above the sample surface. And then we have a mass spectrometer. So we have a device capable of analyzing charged particles on the basis of their mass. And we're trying to separate 87 strontium from 86 strontium. And one of the issues in doing this is that apatites will have everything else in them too, right? They have calcium, phosphorus, and other stuff, some of which won't come off as neutrals, but as ions, and we're first off going to get rid of them. So we're going to use the instrument to get rid of that until we just have a cloud of neutral particles hovering above our sample. This is all happening in the time scale of about, a couple hundred nanoseconds, so this is all happening relatively quickly, so that's why we can talk about a cloud of neutrals sitting here, because they're actually trying to fly off, but we're doing this much faster than they can leave. And so we're then going to take lasers, and these lasers are tuned to a so this is strontium here, this is the ground state, so the neutral atoms all start out here. The first laser is going to hit them, bump the electron into an excited state, give it some energy, and the second one is going to take it out, and we're just going to produce ionized strontium. Then, once we've made the ionized strontium, we can inject it and analyze its mass, and basically just count how much 86 strontium is there, how much 87 strontium is there, and then we can perform division to get the 87 to 86 ratio. Here's what the instrument looks like in AutoCAD, based on the time in it. So these are the posts on which it was built, with vibration isolation. Then they got some laser tables. There is the sample stage sitting here. There's the sort of the flange. There's the housing that goes around it where the laser light's going to come in. Got to introduce a way to get the sample in, so there's the sample introduction system. Here's the door, you put the sample in. You use this arm to shove it into the main chamber. You're going to need a whole lot of vacuum pumps because shooting ions, right? If you have a lot of air and gas in your system, the ions aren't going to fly straight. They're going to collide with the gas molecules. Not a pretty situation, so you're going to need some vacuum pumps. Make it really low pressure so that the ions can fly without colliding with stuff. Then we're going to need a way to image our sample. So we're going to add an electron gun so that we can take a look at our really tiny spots. Seeing a 1 micron image with an optical microscope is really hard. Using electrons is much easier. Here is a gallium gun. This can also be used to remove material. We're not really going to spend much time talking about it. Going to have to add some more stuff. So the ions are going to fly up and get bent back around, so we're going to have to add a place to put the detector. This is the thing that's going to turn the ions around. So the ions are going to be created here by laser light coming in this way, fly up into this device and get turned around. So this just basically has a strong electric field, and so when the charged ion comes into it, it's going to feel that voltage gradient and want to get turned around. And get turned around into our detector, which we've now inserted here into its resting place. Got to cover that all up in a tube to give it some mechanical support. Here's an optical viewport where the desorption laser is going to come down to shoot into the sample. We can also have an optical microscope to look at our sample. So we've got to add a whole bunch of stuff for that. This is the desorption laser. So this is what's going to remove the material, coming around, getting bent. Laser light comes up, goes into the instrument, and hits the sample. It's got a long way to go. And this is the optical camera. This is the optical microscope looking at it. Enclose all of that so we don't have laser beams flying through the lab. Then these are the 3 lasers that are going to drive our 6 lasers that we can use for ionizing things in the instrument. So then we add in our 6 lasers. These are all home built, so these were assembled here in Chicago. And so each of these will come out, will be split, and then these lasers here are there to give you a lot of light, laser light, at very specific wavelengths so that we can ionize the elements we want and not other stuff. This complicated setup here is just to get them sort of into the instrument. If you can see the faint lines, you can actually see the laser light come around, get bent, put into a single line, and kind of fly through the instrument this way to intersect this neutral cloud. And this all has to be aligned painstakingly. And has to be redone when we switch elements. Then we cover it because, again, you don't want a lot of laser light flying through the lab. And so that's sort of what it looks like. Here are some dimensions in meters. So this is quite a big thing. For those of you who prefer pictures, it's a really hard instrument to take a picture of. But here are the lasers for the ionization. The lasers are first green, then we make red light, then we make whatever color we want out. So we're going to often use sort of blue or purple light. Gets bent around, comes in from back here, and then this is the mass spectrometer. So the ions are created here, fly up, fly back down. LiDAR ions fly faster, so they make it to the detector first. They win the race. So the 86 is going to arrive before the 87. And that's the entire principle upon which this works. There's just a really fancy counting system. There's a lot of power supplies and electronics. There's the desorption laser. And there's people working at the computer to control the instrument. So we have 6 tunable lasers, so we can analyze anywhere between 1 and 3 elements at a time. You tend to need about 2 or 3 lasers per element. For strontium, as I showed you, we need 2. First one at 460 nanometers to bump it up into an excited state, and then the second one to kick the electron off and make an ion. And then we're going to have to pull it out into the instrument. And so, since these are some of the first measurements that were done with this technique, especially for terrestrial samples, wanted to prove that it works. So 87 rubidium and 87 strontium have the same mass. This is obviously a problem if you're separating stuff based on mass. It's really hard to separate them. So we took a sample that has equal amounts of rubidium and strontium, and these are the strontium isotopes. So this is the mass here. These are the strontium 84, 86, 87, and 88 peaks, roughly in the right abundance. But what I want you to notice is this is a log plot. We didn't ionize any rubidium 85. We don't see any counts at mass 85. And so we know that there aren't any on mass 87, so we don't have to correct that. We can separate strontium and rubidium because our instrument only ionizes one and not the other. It can selectively do that because we're using finely tuned laser light to do this. So that's great. So we can just sort of make the measurement. We don't see any other nasty peaks that you might envision. For example, you can add up 2 calciums and get into this mass range. That's kind of annoying. But we don't have that problem either. We're really only seeing strontium in this signal. Then it's a new technique, so we need to prove we can make the measurement using standards. These are the red are one set of apatites we use as our primary standard. This is just how many atoms of 86 we measured. This is the 87-86 ratio. So we corrected everything to the true value of Durango of 0.706. And then we analyzed somatic apatite, and look, we get about 0.712. That's great. That's the known value from other analyses. So we can make the measurement, we can make the measurement accurately, and we get the right answer on samples where we know what the answer should be. So we can now take this and say, we're going to look at these old zircons, we're going to look at the apatites in them and measure their strontium isotopes and see what they tell us about the early Earth. So we're looking at 3.8 billion-year-old zircons, so here's just ages of zircons versus how many they found in a study from Nuvvuagittuq. So we're going to look at zircons in this age range. Remember, this is where I've shown you all that lovely samaric neodymium and lutetium hafnium data, so we've got a lot of other data to go with. This is where it was claimed that it was a mafic precursor that separated early in Earth's history, and that this first proto-crust that made these samples was mafic. So, if you look on the back, we should be expecting to find the rubidium-strontium ratio of a mafic rock is really low, right? 0.1, something that is not going to evolve isotopically. So isotopically, we're expecting to measure the same thing as the mantle. We're going to expect to measure something like 0.7. On the other hand, if it's a felsic reservoir, if you look at the back, right, it might have a rubidium-strontium ratio of 1 or 10 or 100. We're going to expect values that are a lot higher than the mantle. So we're going to analyze this, and so this is the expected result is somewhere around 0.7 if these inferences of a mafic reservoir are correct. And there's the data. So we didn't find that, which was really interesting. So here are some evolved back from 4.4. This is a reservoir with a rubidium-strontium ratio of 0.5, 1.65. If you look at your plots on the back, right, these are sort of high silica rocks. And they can evolve to sort of explain the range in the data that we see. So these are apatites in zircons at that age, and in order for the strontium isotopes to be this high, you would need, sort of 600 million years of evolution in a rock that's got this kind of a rubidium-strontium ratio, and you can look in the back and see what kind of silica values that gives you. That gives you really high silica rocks that you had a felsic crust there. So, out of time, I'm actually more or less going to skip these. These will be online, but the main point of this one is that as you alter basalt, the rubidium-strontium ratio goes up. So this is rubidium-strontium, this is rubidium in concentration. This black line is what happens when you alter basalt. And one of the claims that people have made as I've presented this work is that, well, altered basalts can have really high rubidium-strontium ratio. These, in fact, are old basalts. And my point is, yes, but those are already altered because it's unlikely. This is not a fresh, nice composition. And rubidium from weathering comes from the continental crust, so you can't weather your basalts. You can't alter it and add more rubidium to it if you don't have a source for rubidium. So, it doesn't work. Other people, like the Kemp et al., 2010, very briefly, they proposed that this was a layer, that there's a layer on the moon called creep, that's potassium, rare earth, and phosphorus enriched. It's enriched in these incompatible elements, so it does have a high rubidium-strontium ratio. But basically, if you look at all the extraterrestrial samples you can find, you get the highest you find the rock with the highest rubidium-strontium ratio. You actually have to find one on Mars, and that's what the red line is here. So it really doesn't explain the data either. So the only viable explanation is that there were some high silica rocks back then, that there was a continental crust, at least some amount, we don't know how much, right? Could have been very little, could have been a lot. We don't really know, but we have existed for some. And so how does this play into with the other data? So this is, again, this is the lutetium hafnium. This is the sample distribution. So they inferred the lutetium hafnium was between 0.02 and 0.03 in the isotopic, so not necessarily the elemental ratio, be slightly different. But these are the rocks that meet this distribution. Some are felsic, some are mafic. Samarium neodymium, again, what explains the data, gave this sort of flat distribution here. And if you look at the rubidium strontium that we infer from the apatites, because the strontium isotopic signature was so elevated above the mantle, you sample the same database, you get this peak here at high values. What I want you to notice is perfectly consistent with this, right? This is no same power. And it overlaps with this other peak in the lutetium hafnium system. So all of the data from Nuvvuagittuq, I would claim, is consistent with the existence of this felsic crust, but that the previous methods simply didn't have the resolving power to uniquely give you this answer. And so there were two possible choices, and people picked one over the other when this one was still supported by their geochemical measurements. So the punchline of today is that we had that first off, here we can measure the strontium isotopes, so we have a new tool to study this. This is work that's been done this calendar year. It was done, these measurements were done sort of in January. And then we had a high silica reservoir, so we had something that looks like a continental crust at 4.4 billion years ago, or within 150 million years of the planet forming, so that this process happened very early. So these models, the continental crust models that are saying, look, there was no continental crust back then, it was absolutely zero, there was nothing, are not in agreement with some of the recent measurements, and in particular with my own measurements. So, for that, I want to thank you, and I'll take any questions. All right. Thank you for coming. Yeah.
One question. The length of the tube, 1 meter, 2 meters.
Excellent question. From my mind, somewhere around a meter, I would say.
That's what I thought it would be. So as you reverse the direction, you get more spreading of the ions.
The spreading gives you two things. So some of the ions will have a little bit different energies than some of the other ions. So a heavy ion that's a little bit faster might show up as a lighter ion, right? Because it's going to win the race. So there's a little bit of energy spread. The turning around has the big advantage that things that are going faster are going to take a longer path through the instrument than things that are going slowly. So it actually realigns things based on energy. So it gets you slightly tighter peaks in the mass spectrum. We don't really use it for that. We just sort of mostly use it to try and get all the ions in one place in a detector, not have the detector hanging out. But the standard thing to use those for is to say that you can get better mass resolving power. So you can get tighter mass peaks on the mass spectrum.
Okay. Yeah, because the momentum will be different for some of these ions, right?
Exactly. And you want to, so the time of flight, yeah.